Hello? Sorry. Okay, so hi everyone and welcome to track 1. Our talk here at 4:30 is how to secure the keyboard chain. And our speakers today are Paul, Amicelli, and Baptiste David. And here they are. Please help me welcome Paul.
So, hi everyone, thank you for coming. Here's Baptiste David and I'm Paul Amicelli. We are from France and we are working on a computer security lab. So today we're going to talk about how to secure the keyboard chain against a certain type of viruses which are keyloggers. So it's all done under Windows, so sorry for the Linuxians. As we don't have so much time, we will quickly see the keyloggers forms and then the main idea of our works with some details, and we will end up with some ideas we had to go further. So, what's a keylogger? Basically, keyloggers are a little piece of software or hardware or whatever you want, which is able to retrieve every piece of information that can be typed on a keyboard. Meaning, for instance, a credit card number, bank account credentials, reports of companies, and so on. They are underestimated since they can nestle everywhere and they are barely invisible. And as we are going to see in a few moments, they're quite easy to develop. So first, we have to see how the keyboard chain works. There are 3 major stages. The hardware part, so basically each key is a switch, and when you press a key, it generates an interrupt with a code called the scan code. And this is handled by the kernel part of the operating system, which consists of a set of drivers. So we have the I-8042 port, which is the driver port, which basically handles every event on the keyboard and on the mouse. And then we have the keyboard class, which allows to extend the functionalities by the keyboard manufacturers. Then this code is handled by the Ring3 part of the operating system, a submodule of Windows, which converts the keyboard code into a Windows message, which will be understood by all the application and the operating system itself.
Well, when you want to make a keylogger, you've got many ways to do it. First, you can create a user mode 1, which is quite easy to develop because it's quite easy to find codes and examples on internet. And in addition, it's really easy to install. It normally doesn't require any specific rights, and it's very good piece of software which is enough to do the job requested. But most of these keyloggers are very well-known malware, so it can be detected by most of the antivirus software on the market. Because they are detected, they are removable from the system, and it's very efficient but not so stronger. If you want something stronger, you can use kernel mode 1. So in fact, it's just drivers which are inserted inside the keyboard driver stack. And it's much more efficient because they've got a prior access to the keystroke press. When the user presses keystroke, the first notified are the driver from the kernel of Windows. So this is why they are first notified. But it's a bit harder to develop because you need to develop a driver and you need to have specific rights, like admin rights to install the driver on the system, and on x64 Windows subsystems, you need to sign the driver, which means for that to have a certificate and stuff like that. So it can be a bit more difficult to broadcast your threat with kernel mode keyloggers. And for antivirus software, it's a bit more difficult to detect because analyzing drivers, it's a bit harder, and to remove, it could be complicated since your driver is running with ring 0 rights, like on antivirus software. So to have something, again, more stronger than kernel mode 1's keyloggers, you can use hardware's keyloggers. In fact, this is the strongest way to have a keylogger. It's almost invisible since it's out of scope of antivirus software analysis. Why? Because antivirus software only analyzes software, which means files on the hard drive of the system. There is no antivirus for hardwares. So it's almost impossible to detect because it's invisible. Hardware keyloggers can be plugged directly to your machine, for example, or already inserted during the build of the hardware by the manufacturers. So it's sometimes very hard to detect with your eyes when you see your computer. Most of the time, this type of keylogger are targeting attack. So it means it's not broadcast to worldwide threat. And this is a bit complicated to use it because you need a physical access to the targeted machine. Once to plug the keylogger first, and sometimes one more time when you need to retrieve information stored inside this keylogger. So the solution we propose today, it's a software library which is as low as possible in the subsystem of Windows, trying to deal with all these type of keyloggers. And the goal is not trying to detect or remove keyloggers. It's the work of antivirus software, and they are free to do it. But our goal is to scramble keystrokes in order to jamming keylogger present in the system if there are. So that's the goal of our system, and we want to fight against keyloggers which have got many possibilities to be inside the system. For example, when you use a user mode keyloggers, from a technical point of view, you have many possibilities to create it. Among the possibilities, you can use the Windows API function to retrieve message from the keyboard, for example, with get asynchronous key state. Or you can register a hook to be notified when a keystroke is pressed, and a callback is called when a key is received on the system. And that's for user mode application keylogger. If you are a driver, you are in the keyboard device stack, and it depends on the altitude you are. It's just a question of priority. If you are an upper filter, you are above the keyboard class driver, and you use a predefined callbacks given by the keyB class driver to be notified routing to handle IRPs when they are received. But you can be lower using a lower filter driver. In fact, you're just above the IHE42 port driver, and you are notified before a keyB class driver. And if you want to be lower, one more time again, you can hook the keyboard interruption descriptor table, the ERQL, to replace the original keyboard interruption, and using this new interruption to manage your keylogger and when it's taped on the keyboard. So this is among all these possibilities, but this one, the last one of ERQL hooking, it's a bit more difficult to use on x64 systems since the patch guard of Windows is tracking and checking the ERQL validity of this table. So normally it shouldn't work on x64 system.
So now about the solution we've developed. We've put the protection driver in the middle of the keyboard driver stack. So why not in user mode? Just because any other application would have the ability to retrieve the keystrokes as driver. So we could have put it in as a higher filter driver, but also by setting up a lower filter driver, we will be able to retrieve the keystrokes. And the final solution will be to hook the interrupt descriptor table, but with the patch guard, it's not a regular solution. So the only place to be the most efficient is to be in the middle of the keyboard driver stack. So if we go a little into details on the keyboard driver stack, when a key is pressed, it generates an interruption which is handled by the interrupt service routine of the IHE42 port driver, which it checks and the scan code and directly forward it to the protection driver. The protection driver encrypts the scan code if it needed, and then gives them back to the IHE42 port driver. And then the normal processing is done. It's queued into a DPC, and then a call of the keyboard class driver is done, and the scan code is pressed to the right of the system, but encrypted.
So about encryption. In fact, the original idea we've got when we started the project was just to simply cipher every keystrokes received by the system. This is not a very new solution or very sophisticated solution, but if you try to do that, it won't work as you expect. In fact, what you observe is that very few keystrokes are broadcast and received by the application of the system. So what does it mean? If you are looking for, you will see that Windows only broadcasts key codes received and that it knows. In other words, It means that unknown key codes are not broadcasted and are inhibited by Windows. So, of course, if you use ciphering techniques, it means you use all possible outputs, code, using the keyboard code. And inside this code, a very small portion of this code are understandable by Windows. So that's why you receive so few keystrokes for application. So it leads us to find another solution, and a solution which only deals with non-keystrokes to be broadcasted on the system. And this solution to perform jamming uses the following idea. The idea is to use substitution and permutation on a set of allowed keystrokes, that is to say, of broadcastable key codes by Windows. We have constituted a whitelist of authorized key code, and we have worked with them on our algorithm to let the key code being broadcast by the system. In fact, we will use the original stream cipher as a pseudo-random number generator, which is used to perform substitution and permutation operation on the allowed set of key codes. And this set is shuffled for each key received on the system, which makes harder to perform cryptanalysis with statistical properties. And with this solution, because it's just a permutation, ciphered key code are broadcast on the system. That was the goal of our solution. Of course, keylogger will receive only randomized key codes. That means they have not the keys shared between the driver and the application which use our API to be able to decipher the received key codes and recalculate the original keystrokes received on the system. We talk about the whitelist of authorized key code, and for example, just on screen is a keyboard, and in green, you've got the keys which are in the whitelist for us until now. It's allowed keystrokes. In fact, that's enough to type a password, because you've got characters, numbers, and symbols, and these keys are all similar on all keyboards all over the world. In Orange, it's keys that could be included inside the whitelist, but they don't directly mean something for the user, like enter or remove or shift. It could be used to improve the number of possible passphrases, but until now it's not inside the whitelist. The white keys, lastly displayed, are not encrypted key, because this key, most of the time, means something for the system. Encrypted, something like Ctrl-Alt-Del, doesn't make any sense, because the user will lose control of his machine very soon. So, most of these keys are not used by password, and most of them also depend on the keyboard manufacturers, from a laptop to gamer keyboards. There is many difference of keys. So to be as generic as possible, we just choose the smallest set of allowed keys. But in the future, it could be much more larger. So to sum up, in fact, with our algorithm, from a theoretical point of view of the input of the algorithm, you've got two possibilities. If the keystroke received is not in the whitelist, it means we have not to make any encryption operation on it, because it doesn't make sense. So it just broadcasts to the system normally, and it won't be touched by our application. And if the keystrokes received is in the whitelist, it means we need to cipher it. So it receives encryption operations, that is to say substitution and permutation, and it follows the process described earlier, that is to say its output on the system. So more generally, if you want to have a good idea also how to use the solution, we've got an API, which is in fact a library stored in a normal DLL, which is used by a client application on the top left of the pictures. At the beginning, the API is made to have the first step to be an exchange of key between the drivers and the application. Once the stream cipher secret key is sharing between the two parts, we can start the protection. That is to say, when a keystroke is received, the protection driver at the left will be notified of the key code. It will perform the encryption operation and broadcast it to keyboard cross driver, which will send it to crss.exe application, which will translate the code into Windows message. The client application will be able to decipher this code because they share the same key with the stream cipher, but another application, which can be a kilohertz, will only see random data because it doesn't make sense for him. From that point, one can say that it's not enough to make protection. Let's take an example. If someone succeeds to insert a driver lower than ours, it means he will receive keystrokes before our protection drivers. So he will be able to perform keylogging operation without being disturbed by our protection driver, which act after. So to give countermeasure to such problem, we have implemented many solutions. First, to detect lower driver, we first monitoring the registry, checking that there is no driver installed lower than ours. And then we monitor during the runtime the keyboard driver stack to check that there is no driver inserted lower than us. At the end, we perform protection against debugging techniques, for example, DLL injection, stuff like that. The goal is to prevent application to get access to the working set of our protected application to retrieve, for example, the stream cipher key shared between the application and the driver. So doing that, we make filtering on process handle access or thread from the process access, etc. At the end, we use self-cryptographic tests to check the integrity of cipher subsystem between the driver and the application. The goal is just to prevent the altercation of cryptographic routines used by both sides. And in addition, it checks the good functioning of the system at the beginning before use. So, is it working? Yep. So, in fact, just for demo purpose, we have created a little application which has two threads, one acting as a keylogger and one acted as a protected application. First, the application and the protected thread, we try to make a connection between the drivers and itself, sharing the key and after acting. So we will try to launch a video. It's very short. So at the beginning, you've got the initialization and sharing the key. That's made. And then following, you've got something typed on the keyboard, and at the left, you've got the random data received by any keyloggers which heard on the system, which keystrokes are pressed, but on the right, you've got the good keystrokes received on the system by the protected application. That was the goal of our library. So to give back.
So now, here is some ideas we had to hack the protection system and to improve it. So, for instance, keystrokes combination. For instance, when the user tip twice an A, it would give an A, or Control A, give an A, or whatever the user wants. Then we had a polymorphic on-screen combination keyboard. The idea between this is to fool all keyloggers, even hardwares. So in fact, it will be virtual representations of the real keyboards, and the user would have to tip on its real keyboard according to the virtual representation. And then, of course, the virtual representation will permute and change every keystrokes according to the output of the stream cipher of the current version of our protection. Then we have time-based keystrokes. For instance, the user would have to press a key according to a timer displaying on its screen. Or like MIDI games, piano keyboards, for instance, press the key according to a certain melody, such thing like that. And the last idea is to keep keystrokes in ring 0 as we are developing it in Ghostscript. So Ghostscript is a fork of TrueCrypt developed in our labs, in which we have removed UK-USA algorithm and put others. So the problem with Ghostcrypt and so TrueCrypt is that the passphrase is in ring 3, while all the encryption system is done in ring 0. So it's really easy to retrieve the passphrase with a DLL injection. So the idea is to lower all this procedure in kernel mode and in order to add a security layer. So in fact, the keystrokes will be internally stored as soon as a passphrase prompt is shown. So the keystrokes stored, and then they are directly sent to the encryption function of the Ghostcrypt. So that way, if one wants to retrieve the passphrase, it would have to be in the kernel, which is much, much more complicated. So the taste of the project, for now, it's a beta version, so it needs more improvements and tests. Obviously, it's free and open source, so it's available on Bitbucket. You have the link below. And if one wants to participate, we will be glad to welcome in the team. So thank you for your attention. If you have any questions, maybe around the beer, or we are on peerlist.com. Thank you again. Yeah.
Is there a way to keep a keylogger from hooking underneath you, underneath your interrupt driver, or can you only detect that, or can you prevent it as well?
We can detect it with the monitoring of the registry of the keyboard driver class. So, as you said, there is two possibilities. The first one is to raise an alarm to the user and saying, hey, there is something odd in the system. This is what happened today. Removing it is possible, but it's quite dangerous because you will broken the keyboard stack device and it could lead to bug check. So it's possible, but it depends on the user option configuration. Yep. So, yes. In fact, it's not broadcast in ring 3 mode, that is to say in application. So if you are an application, you won't be able to see it. But if you are a driver, you will be able to see it, to see these unmeaning codes. So I think it's answer to your question. Okay, thank you. Okay. So thank you for your attention, and we are available for a beer or something stronger if you want. Thank you.
Thanks, guys.